Hello students, in past few classes we have studied some important concepts about the topological spaces and the basis for a topology, which mainly includes the definition of a topology, definition of a topological space, definitions of the discrete and indiscrete topology, finite complement topology, finer topology, coarser topology, strictly finer topology, strictly coarser topology, and comparable topologies. Then in the article basis for a topology, we have also defined basis for a topology on a set X and the topology generated by basis. We have also studied some results on the basis for a topology and solved some examples on that. We have also defined standard topology, lower limit topology, and K topology on the real line and defined the subbasis and topology generated by the subbasis. These were the main things that we have studied in the past few classes. And in the last class, we have solved one example on the topology, in which we have shown that the intersection of topologies on a set is again a topology on a set, which means that if X is some set on which we have a family of topologies defined on the set X, then the intersection of that family is again a topology on X. Means if family to alpha is a family of topologies defined on some set X, then intersection of to alpha is again a topology on the set X. Now in today's class, we will solve one more example, and this example is important in clarifying the concept of the topology. So let us solve that example. Next example is, if X equal to the 3-point set containing elements A, B and C, and let τ1 is the collection having members the empty set phi, the complete set X, the singleton set A, 2-point set A, B, and τ2 be the collection having elements the empty set phi, the complete set X, the singleton set A, and the 2-point set B, C. Then find the smallest topology containing τ1 and τ2 and the largest topology contained in τ1 and τ2. Here these words containing and contained are very important. So we'll solve this example. First of all, we'll find out the smallest topology containing τ1 and τ2. Containing τ1 and τ2 means τ1 should be subset of that topology as well as τ2 should be subset of that topology. And let us denote that topology by τ. Let us solve this. Solution is given the set capital X is equal to the 3-point set containing members A, B and C. τ1 is the collection having members empty set phi, the complete set X, the singleton set A, and the 2-point set A, B. And also we have given the second collection τ2, which is the collection having members phi, complete set X, 1-point set A, and the 2-point set B, C. Let τ be the smallest topology containing τ1 and τ2. Let τ be the smallest topology containing τ1 and τ2. Then as τ contains τ1 as well as τ2, then clearly τ1 and τ2 both will be the subsets of τ as well as their union Tau1 union Tau2 will be a subset of Tau. So therefore Tau1 union Tau2 is contained in Tau. So first of all we have to compute Tau1 union Tau2, but Tau1 union Tau2 is equal to, take the union of Tau1 and Tau2. Tau1 union Tau2 equal to the empty set phi, then the complete set X, then the singleton set A, then the 2-point set A, B, and the 2-point set B, C. So like such we'll get the Tau1 union Tau2. So Tau1 union Tau2 is equal to, this is the collection containing members, the empty set phi, then the complete set X, then the singleton set A, then the 2-point set A, B, and the 2-point set B, C. This is the Tau1 union Tau2. Now, as we require the smallest topology containing Tau1 and Tau2, so therefore, first of all, we have to check whether this Tau1 union Tau2 itself is a topology on X. If this itself is a topology on X, then this is our answer of the first question. And if this Tau1 union Tau2 is not a topology on X, then we have to insert some additional members in Tau1 union Tau2 such that it will become a topology. And such additional elements which are to be inserted should be as less as possible. First of all, we'll check whether this Tau1 union Tau2 itself is a topology on X or not. For that purpose, observe here, this Tau1 union Tau2 collection contains the empty set phi and the complete set X, which means that the first condition is satisfied. Then second, and to check the second condition, we have to consider all possible unions of elements of Tau1 union Tau2. And as we have discussed in detail while studying the definition of the topology, that to check the second and third condition means for union and intersection, empty set phi and X is not necessary to check for the union and intersection. So let us move further. So union of this singleton set A with the 2-point set A, B is the 2-point set A, B which is already present here. Then union of this singleton set A with the 2-point set B, C is the A, B, C, means the complete set which is already present here. And finally, the union of the 2-point set A, B with the set B, C is the set A, B, C which is equal to X, which is already present here, which means that here the second condition is satisfied. Now we have to check the third condition, which is about the intersection. And again for the intersection, it is not necessary to consider the empty set phi and X. So the intersection of singleton A with the 2-point set A, B is the singleton A which is present here. Intersection of the singleton A with the 2-point set B, C is the empty set which is already present here. And finally, the intersection of 2-point set A, B with the 2-point set B, C is the singleton B, which is unfortunately not present in this collection, which means that this Tau1 union Tau2 is not a topology on X. So we have to insert one additional member, which is the singleton set B, and let us check once again that whether it becomes the topology or not. So we'll insert that additional member singleton set B in this earlier collection, and we'll get the empty set phi, then the complete set X, then the singleton set A as it is, then the singleton set B, this additional member we are inserting here, then the 2-point set A, B as it is, and the 2-point set B, C as it is. So like such we'll get this collection. Now once again we'll check whether this collection is a topology or not. Clearly this collection is a superset of Tau1 union Tau2. Therefore it contains both the topologies Tau1 and Tau2. Next we'll check whether this is a topology on X or not. First of all, first condition is satisfied as empty set phi and complete set X both are present here. Then we'll go for the union. Union of A and B is the 2-point set A comma B which is present here. Union of A with the B comma C is the set ABC which is equal to X which is already present here. Union of A with B is the 2-point set A comma B which is present here. Union of A with the 2-point set A comma B is the 2-point set A comma B which is already present here. Union of A with the 2-point set B comma C is the set ABC which is X which is already present here. Then the union of B with the 2-point set A comma B is the 2-point set A comma B which is already present here, and union of B with the 2-point set B comma C is the 2-point set B comma C which is already present here. And finally the union of 2-point set A comma B with the 2-point set B comma C is the set ABC which is already present here, which means that second condition is satisfied here. Now we'll move to the third condition. We'll check the third condition. Now intersection of first two sets means singleton A and singleton B is the empty set which is already present here. Intersection of singleton A with the 2-point set A comma B is the singleton A which is already present here. Intersection of singleton A with the 2-point set B comma C is the empty set which is already present here. Intersection of singleton B with the 2-point set A comma B is the singleton B which is present here. Intersection of singleton B with the 2-point set B comma C is the singleton B which is present here. And finally the intersection of 2-point set A comma B with the 2-point set B comma C is the singleton B which is already present here, which means that this collection is a topology on X. And as this collection contains TOE1 and TOE2 and it is obtained by inserting only one additional member in the TOE1 union TOE2. Therefore, this is our required topology. Therefore, TOE, which is equal to this collection containing members empty set phi, then the complete set X, singleton set A, singleton set B, 2-point set A comma B and 2-point set B comma C is the smallest topology. So this is the smallest topology. Smallest topology containing TOE1 and TOE2. So like such we have solved first question of this example. Now we will solve the second part of the example, in which we have to find out the largest topology contained in TOE1 and TOE2. Contained in TOE1 and TOE2, which means that we have to find out a topology on the set X in such a way that the topology should be a subset of TOE1 as well as it should be a subset of TOE2. Means it should be a subset of both TOE1 and TOE2, which obviously means that it should be a subset of TOE1 intersection TOE2. So therefore, for finding that topology, first of all we have to find out the intersection of TOE1 and TOE2. Let TOE dash be the largest topology contained in TOE1 and TOE2. Then clearly TOE dash is subset of TOE1. Contained in TOE1 means subset of TOE1, and TOE dash is contained in TOE2 also, means TOE dash is a subset of TOE2 also, which implies that the required topology TOE dash is a subset of TO1 intersection TO2 also. So therefore, first of all, we will find out the TO1 intersection TO2. We have TO1 equal to the collection having members phi, x, singleton A and 2-point set A, B, and TO2 is equal to the collection having members phi, x, singleton A and the 2-point set B, C. Therefore, as told earlier, first of all we will find out TO1 intersection TO2. Therefore, TO1 intersection TO2, it is equal to, observe here both collections TO1 and TO2 contains the empty set phi and the complete set x. Therefore, TO1 intersection TO2 will again contain phi as well as x. Also, the singleton set A is present in both sets TO1 as well as in TO2. Therefore, it will be present in TO1 intersection TO2 also. And the 2-point set A, B is present in TO1, but however it is not present in TO2. Similarly, the 2-point set B, C is present in TO2, but it is not present in TO1. Therefore, neither the 2-point set A, B is a member of TO1 intersection TO2, nor the 2-point set B, C will be a member of TO1 intersection TO2. Therefore, TO1 intersection TO2 will be the collection which will consist of only 3 members: the empty set phi, the complete set x, and the singleton set A. Therefore, we have TO1 intersection TO2 equal to the empty set phi, the complete set x, and the singleton set A. This is our TO1 intersection TO2. Now, as we have to find out the largest topology contained in TO1 and TO2, therefore, first of all we have to check whether this TO1 intersection TO2 itself is a topology on X or not. If this TO1 intersection TO2 itself is a topology on X, then this is our answer. And however, if this TO1 intersection TO2 is not a topology on X, then from this TO1 intersection TO2 we have to take out minimum number of elements in such a way that the resultant set will become a topology on X, and we have to take out the minimum elements only. First of all, we will observe that whether TO1 intersection TO2 itself is a topology on X or not. Observe here the empty set phi and the complete set X both are present in TO1 intersection TO2. Therefore, first condition required for being a topology is satisfied. Now we will check the second and third conditions. First of all, we will check the second condition, which is for the arbitrary union. Observe here, union of empty set phi with the complete set X is the complete set X which is already present in TO1 intersection TO2. Union of empty set phi with the singleton set A is the singleton set A which is already present in TO1 intersection TO2. Union of complete set X with the singleton set A is the complete set X which is already present in TO1 intersection TO2. And finally, union of empty set phi, complete set X and singleton set A is the complete set X which is already present in this collection TO1 intersection TO2. Therefore, if we take any subcollection of elements from TO1 intersection TO2 and form its union, then that union is always a member of TO1 intersection TO2, which means that the second condition is satisfied. Now we will check the third condition, which is for the finite intersection. Intersection of the empty set phi with the complete set X is the empty set phi which is already present in TO1 intersection TO2. Intersection of empty set phi with the singleton set A is the empty set phi which is already present in TO1 intersection TO2. Intersection of complete set X with the singleton set A is the singleton set A which is already present in TO1 intersection TO2. And finally, intersection of empty set phi, complete set X and the singleton set A is the empty set which is already present in TOE1 intersection TOE2. Therefore, we have shown that the intersection of finite number of members from the collection TOE1 intersection TOE2 is again a member of TOE1 intersection TOE2. This shows that the third condition is also satisfied. Therefore, we have shown that the collection TOE1 intersection TOE2 satisfies all three conditions required for being a topology, and therefore the collection TOE1 intersection TOE2 itself is a topology on X, and this TOE1 intersection TOE2 is contained in both TOE1 as well as TOE2. Hence, our required largest topology contained in TOE1 and TOE2 is this TOE1 intersection TOE2 itself. Hence, we conclude that TOE', which is the required largest topology contained in TOE1 and TOE2, is nothing but it is TOE1 intersection TOE2, and which is equal to the collection which consists of the empty set phi, the complete set X and the singleton set A. This is the required largest topology contained in TOE1 and TOE2. So in this way, we have solved the second part of the example also. So in the first part of this example, we have obtained the smallest topology which contains TOE1 as well as TOE2, and it was TOE, which was the collection consisting of elements the empty set phi, complete set X, singleton set A, singleton set B, 2-point set A, B and 2-point set B, C. This is the smallest topology containing TOE1 and TOE2. And in the second part, we have obtained a largest topology contained in TOE1 and TOE2, and it was the collection consisting of the empty set phi, the complete set X and the singleton set A. In this way, we have solved this example. We'll stop here and we'll continue in the next class. Thank you.